All right, please bear with me. Um, I'm recording this lecture since campus is closed. This is the fourth time I'm attempting to record it. Due to weather and other things, a lot of issues have come up and it has not worked. So I'm hoping this time it works. But yeah, because of this, I'll probably be a little bit quick. I'll also be jumping off the PowerPoint occasionally to check the screen to make sure that I'm still recording so I don't have the same problems that I've been having. Anyway, that being said, let's jump into this. Let's pull up the PowerPoint. Um, so let's do announcements and reminders as we usually do. Um, I got an email from an online 101 student, which prompted me to explain this to you. So I guess really, if you're an in-person student, this does not necessarily pertain to you. This is for students who are not currently enrolled in the in-person spring 2026 101 course. So as you're watching these, when I give information about due dates or specific assignments, it might not pertain to you if you are an online student. So the example, this is a great question this student asked, and I'm so glad they did. The online student was asking about pre-labs and had no idea what pre-labs were, which makes sense because online students, you don't have to do pre-labs, right? So your version of the lab does not have all that information broken down into pre-lab versus lab. Like for you, you still have the same questions, except it's just all answered at once, right? It's not broken down. Meanwhile, in-person students need to do the pre-lab first before they can come to lab, right? Because I want to make sure they're prepared before they come in and do experiments. So that's just one example. So yeah, do if you have any questions about that, do what that other student did and email me. You can confirm or ask questions if you have them, confirm if you need confirmation. Anyway, like I mentioned, we were having weather, as I'm sure you know. Therefore, due dates may be extended. And I say maybe because really there's nothing due until Friday, right? Last Friday was the last due date. So lab two was due on Friday. Excuse me, lab one was past due on Friday. Um, and so was the pre-lab for lab two. So that was before the weather. So I'm not extending due dates necessarily for that. I will say though, since it is early in the semester, I will accept late work, but there'll probably be a small penalty. And then moving forward, again, like I mentioned on day one when we had the syllabus discussion, there won't be any late work accepted. But anyway, so again, due dates moving forward, I might have to make some adjustments for what's due this Friday, but we'll cross that bridge when we get there. I want to point out on a related note that I don't know what the weather is going to do, so we might not meet on Wednesday. Campus might be closed, or campus might be open, and I might not be able to make it to campus, or campus might be open and I might be there, but you might not be able to make it. Right? So, before you come in, as always, I always say make sure you check your emails and the course announcements. Like I posted today, hey, we're not going to be meeting. So same situation. Make sure you check first before you come in. Likewise, like I said, I don't. We might be there, but that doesn't necessarily mean you have to be there. So if you're snowed in, you can join us online, or you can watch the video at a later date. I don't want you to put yourself at risk. Likewise, if we can't meet on Wednesday, or if you can't join us on Wednesday for lab, there's an online version of lab two, and I'll provide that to you when the time comes. So you might have to do that instead of the in-person lab. It's almost identical. It's almost exactly the same. The only difference is at the very end, the in-person students do a pH experiment where you physically mix acids and bases and you change the pH of these solutions. But the in-person students don't have that because they don't have acids and bases. So they have some sort of a little virtual experiment that they do. So that's the only difference. And I say that because if you've already done the pre-lab for lab two, which you should have, because it was again past due on Friday, then you might be frustrated and be like, oh, now I'm gonna have to do a completely different pre-lab. And you don't, right? So the pre-lab questions that you've already done, you can just copy and paste those directly into the online version of the lab because it's the same thing. As always, I'll remind you that attendance is mandatory. Participation is graded. Um, as usual, I'm going to be giving a set of attendance words throughout the video, and I'm going to ask you to email me those words. Except the only thing that's different now, if you're an in-person student, usually that is for extra credit. Today, since you are watching this on a video, now it's required, right? So make sure you send me an email. Write down every time I say a screenshot. Write down every time I say an attendance word. Take a screenshot of it, and then at the end of the video, you're going to send me an email that has all those attendance words, all the screenshots, and then make sure you don't forget this. You need to ask me one question about the material covered in the lecture. Even if you think you understood everything, just think of it as a question that I could ask on a quiz or an exam based on the information covered in this lecture. Yeah, speaking of which, the first word for attendance, I'm about to circle it. So get ready to write it down. Get ready to take a screenshot. And it is the abbreviation for Wednesday, capital W, capital E, capital D. Write that down, take a screenshot. Normally I would pause and give you time to write that down and take a screenshot, but this is on a recording, so you can pause it yourself if you need to. The last announcement is that exam one will be next Friday. So not this coming Friday, but next Friday on February 6th. We will be meeting as usual at 8 o'clock a.m. in H205, like we always do. We're going to be there from 8 to 8:50. You're going to need to bring your computer, and I would also recommend bringing your cord so your computer doesn't die. But yeah, we're all going to be taking, even though it's on the computer, we're going to be doing it in person because I want to make sure that it's a closed book exam and you're not using notes and you're not using your textbook and you're not looking things up on ChatGPT, right? So be prepared for that. Obviously, you're only going to have 50 minutes to take that exam. So if you're somebody who doesn't like time limits, contact me now, right? We've got about 2 weeks, right? Contact me now and we can make arrangements for us, you and I, to meet at a different time, right? So if you and I can meet at a different time and I can ensure you're taking closed book exam, I don't care how long it takes you to take it. The only reason we have a 50-minute limit on Friday is because we only have the room for 50 minutes. After that, someone else is going to need the room. So anyway, yeah, let me know if you have any questions about that. Sorry it took so long with the announcements. Let's finally jump into the material. We left off talking about bonds. So before we talk about the new concepts, the covalent bonds, I want to remind you of a few things that are important and to jog your memory, because if you don't remember this, the one I'm about to teach you wouldn't make much sense. So as a reminder, when we're talking about chemistry in this 100 level course, as far as we're concerned, chemical bonds, right? It's all about the electrons. It's the electrons that are involved in these chemical reactions. And as far as we're concerned in this course, it's all about the octet rule, right? The octet rule, which is basically saying these atoms want to have a full outer ring. They want their outer electron ring to be full of electrons. And as far as we're concerned, that is what drives these chemical reactions. This is what makes these chemical bonds. It is actually a little bit more complicated in real life, but this is a 100 level course. So as far as we're concerned, that's the story. Speaking of which, if you want to look into it some more and look into the deeper answer, the deeper reasoning, you can for extra credit. Make sure you include your sources. But anyway, before we move forward, to remind you, when I talk about a full ring, when we draw these atoms, we draw an inner ring, and I'll give you some examples moving forward, but I'm not going to do it at this moment. We draw an inner ring. I'll go ahead and draw it. The inner ring holds 2 electrons. Right. So if anything happens to have more than 2 electrons, then it's going to have another ring, and that one's going to hold 8 electrons, and so on and so forth. So as far as we're concerned in this course, again, and this isn't necessarily the case, but the first ring always holds 2, and every subsequent ring after that always holds 8. That's the information you're going to need to answer questions in this course. Again, it's not 100% accurate, but it will suffice for this course. Another thing to point out is, like I keep saying, the outer ring holds 8 electrons. Your textbook also does say 4 pairs of electrons, which is essentially the same thing. But I don't know. So you can think of it however you want. But to me, 8 seems easier based on the problem solving that you're going to have to do. So 2 on the inside, 8 on the outside. Don't forget that. And again, octet rule. They're looking for a full outer ring to become stable. Now that I have that reminder out of the way really quickly, let's look at ionic bonds, which we've already talked about. Hopefully this is simple. It's in the name. Ionic bond, right? It's a bond between ions. What is an ion? An ion is an atom that's either given up an electron or taken an electron, right? And if you give up an electron, you've lost something negative, so you become positive. If you take an electron, you gain something negative, so you become negative, right? So they are charged. That's what an ion is. So what happens, like I said here, they give up an electron, you know, this sodium, right? It needs 8 electrons on its outermost ring, but it only has 1 in its outermost ring. So instead of gaining 7 more electrons, it can just get rid of that outermost ring. And therefore the next one, right? So those are what, ring 1, ring 2, ring 3, right? So it gives up that electron right now. So now ring 2 is the outermost ring and it is full, right? Meanwhile, this chlorine atom, you know, you can count it if you want. It has 7 electrons on its outermost ring, meaning it needs 1. So again, sodium needs to give 1 up. Chlorine needs 1. They help each other out. When sodium gets rid of the electron, it becomes positive because it got rid of something negative. That chlorine, when it gets the electron, it becomes negative because it gains something negative. Gains something negative. And opposites attract, right? So these positive things attract these negative things, and that's what an ionic bond is. You can download the PowerPoint and watch it in action if you want. Watch it being animated. We've already talked about the announcements and reminders, so finally we are caught up with about 40 minutes left. All right. So let's talk about covalent bonds. We're only going to talk about 3 types of bonds. Again, the first one was ionic bonds. We're done talking about that. The next one's covalent bonds. And this is when the atoms are sharing electrons. Your textbook gets very specific and says sharing 1 or more pairs of electrons. And I'm not even going to get that specific. The idea here, I want you to know that they are sharing electrons. They're not giving them up. They're not taking them. They have joint custody, so to speak, right? They're sharing these electrons. Covalent bonds are the strongest and most common. I'm going to underline strongest because you do need to know that for the exam. And that'll be important later in the semester, the fact that covalent bonds are the strongest. When we talk about DNA, that's going to be very important. But for now, well, it's also important for the exam too. Covalent bonds are the strongest. Technically, when bringing atoms together with covalent bonds, we call that a molecule. I'm not going to test you on the definition of a molecule, but you need to know what a molecule is because we will be using that word a lot, and we will be discussing many different types of molecules. Again, like I just talked about earlier, the whole purpose here, just like with an ionic bond, is it's trying to fill its outer electron shell, aka a valence shell. That's the first time I've said this in this lecture. That outermost shell, we call it the valence shell or the valence ring, if you will. But again, it's trying to fill that outer ring, not by giving up electrons or taking electrons, but by sharing them. There are 2 types of covalent bonds. The first one is a little bit less important as far as studying for the exam, and that's called a non-polar bond. This is when the electrons are shared equally. You might be wondering, what does that mean, shared equally? Well, I'll discuss that moving forward. The other type of bond, and I wish we were together because I would love to ask you to see who could guess, and hopefully common sense would lead you to this. If one type is non-polar, the other type is polar. And as you might imagine, they're the opposite of each other, right? With non-polar bonds, the electrons are shared equally. Polar bonds, the electrons are not shared equally. Again, you might be wondering what that means, but we will discuss it later in this lecture unless something goes wrong. And speaking of something going wrong, I'm going to escape out of here. I'm going to make sure that my video is still recording. And it is, so let's get back to it. All right, moving forward, I will give you the next word for attendance. And it's not going to be a word at all, but a number. And that number is the number 6. So write that down, screenshot it. I should see a screenshot that has the number 6 circled on it. Moving forward, because again, I know you can pause this. It's a video, so I'm not going to give you time to do that. So this example I'm going to give you, you do not need to memorize anything here. This is an example that's going to show you how to solve a problem or answer a question, or in the case of lab 2, which we have this week, how to fill out the table for lab 2. So in the question, or in the exam, if this were to be a question, I might ask you this. I might ask you, how many times can carbon bond, or any element, right? I might just give you the element and ask you how many times it can bond, right? And also, if I give you the element, and I'll also give you the symbol. So carbon symbol happens to be C. And I'll also give you a periodic table of elements so you can look this up for yourself. So what would you do? You would look up carbon. You would see by looking it up that its atomic number is 6. And hopefully, as you remember from the last lecture, whatever the atomic number is, by definition, that's how many protons it has, right? Protons define the atomic number. So helium, for example, has 2 protons, therefore its atomic number is 6. Hydrogen has an atomic number of 1, therefore it has 6 protons, right? So notice too that I never said anything about it being charged. I didn't say this carbon was positive or negative or anything like that. Therefore, I don't even have to say it, but it's neutral. If I don't say anything about it having a charge, that means it's neutral, which means it has an equal number of protons and electrons. So again, if you know its atomic number is 6, therefore it must have 6 protons. And if it's neutral, therefore it must have 6 electrons. Then what you're going to need to do, and for the exam, I'll provide you with scrap paper and something to write with, but you may need to draw this out if you can't do it in your head. But you're going to draw the first shell. And it's already drawn here, but imagine it wasn't full, right? Imagine I'm doing this, right? So anyway, you draw the first shell. Then you put in your 2 electrons, right? You've drawn 2 electrons, right? Then you think, all right, well, it's 6 electrons total. I've drawn 2. So how many are left? 6 minus 2 is 4. So then you draw your next ring. Then you draw however many are left. 1, 2, 3, 4. There we go. So now we know that there are 4 valence electrons. 4 electrons on the outermost shell, right? 4 electrons on the valence shell. I'm saying the same thing in different ways. We know that it has 4 electrons out there. We also know that it needs a total of 8, right? So if it has 4, it needs a total of 8. How many does it need, right? So 4 plus what equals 8? And it needs 4 more, right? Therefore, as far as we're concerned in this class, and this is not always correct, but for the purposes of the questions I'm going to give you, however many electrons it needs in the outermost shell, that's how many times it can bond. So really quickly before I move forward, these numbers for the test, right, when you get these questions or when you're filling out the table, these numbers will always be the same, these 3 numbers. The atomic number, which equals the number of protons, and since it's not charged, also equals the number of electrons. Also, these 2 numbers will always be the same. The number of electrons that it needs to become filled is always the same as the number of times it can bond, at least in this class. I will point this out because I don't want anybody to get confused. Maybe carbon's not a good example for this because it just so happens that the number of electrons this thing has on its outermost shell, which is 4, is also how many times or how many electrons it needs to fill its outer ring and how many times it can bond. But that's not always the case. Really quickly, as another example, oxygen's, well, if we talk about oxygen, its atomic number is 8. Therefore, it has 8 protons. Therefore, it has 8 electrons. Therefore, it has 2 on the inner. 8 plus what equals 2? 6. Therefore, it has 6 on the outermost shell. Therefore, and again, it needs a total of 8. So if it has 6 on the outermost shell, it's going to need 2 more. Therefore, it can bond 2 times. So again, in carbon, yes, these numbers match, but in every other one, they won't. I wish we were meeting together because I would ask you if you have any questions about this before moving forward, but you can just email me if you do. I also want to point this out. You're going to be very familiar with a structural formula. In Lab 2, you're going to have to draw some structural formulas. They should look like this. They should not look like this. They should not look like this. They should not look like this. If they look like anything other than this, I can only assume that you looked it up. And I don't want you to do that because the goal, just using formaldehyde, which is what this is as an example, it's not important that you understand the structure of formaldehyde, the idea is for you to be able to problem solve and learn how these things bond together, right? So make sure you're only using the structural formula. Another reason I want to bring this up is even though you're going to be dealing with structural formulas in lab, you may see a space filling model in the textbook or a ball and stick model or an electron configuration, whatever it may be. I just want you to know those are the same molecule. They're just presented differently. Yeah, so don't let that confuse you. All right, another good thing I want to point out here, like we said in the previous slide, carbon can bond 4 times. And I don't want you to be confused because if you look at this picture right here, right, and if you're not familiar with chemistry, this might be confusing because this carbon is bonded to 1, 2, 3 atoms. And I just said carbon can bond 4 times. Actually, a better way of saying it, I keep saying can bond. As far as we're concerned, it will bond. It has to bond 4 times. So you might be wondering, well, if it can bond 4 times, then why is it only bonded to 3 other atoms? And this is where these lines come in. Each one of these lines is a covalent bond. So we have one covalent bond here, the second covalent bond here, a third covalent bond here, and a fourth covalent bond here. So you can see this carbon is double bonded to that oxygen, right? So it still has a total of 4 bonds, even though it's only bonded to 3 atoms. So a different example might be methane. Methane is CH4. And this is also something you're going to need to know for the lab. So I'll go ahead and bring this up. If I were to ask you to draw CH4, now these are organic molecules that we're working with, so it's always based on the carbon, right? This is going to look horrible, but I'm going to try to do it. Forget that one. That line is horrible. All right. So it's always going to have a carbon in the middle and everything else is just based around that. So I know carbon can have 4 bonds. So I'll just circle it and put the other 4 atoms around it. All right, there. Now let me draw the lines in. And there we go. Now we have CH4 because C means 1 carbon, H4 means 4 hydrogens, right? So anyway, this is a different example. In this case, just like in the case with formaldehyde, it still has 4 bonds as it must, but this time you can see it's bonded to 4 different atoms instead of 3. And I'll give you one more example. Carbon dioxide, CO2. Again, everything's based on the carbon, so I'll just draw a carbon here, and then I'll arbitrarily, I'm going to draw one here, draw an oxygen here, and draw an oxygen here. So then I'm going to connect the dots. All right, there we go. But oxygen needs to bond 4 times. This is only 2 bonds. So let me just draw another little covalent bond there. And there we go. 1, 2, 3, 4 bonds. Right? This carbon, even though it's only bonded to 2 atoms, it still has the required 4 bonds. It's very important stuff. And really quickly, even though I've hinted at it, I want to explicitly state this because you're going to need to know this for the lab. This is how you can change, or not change, but you can take the molecular formula, which is the letters and the numbers, and figure out how many of each atom it has, right? So CH2O, that means there's 1 carbon, 2 hydrogens, 1 oxygen. CH4, 1 carbon, 4 hydrogens. CO2, 1 carbon, 1 oxygen. 1 carbon, 2 oxygens. Another example, and we'll talk about this one hopefully later today. Hopefully I can get far enough in this lecture to do this. But H2O, that's one we're all familiar with, right? That means there's 2 hydrogens, 1 oxygen. So that's a skill you're going to need for lab 2. So let's move forward. If you download the PowerPoint, you can watch this little animation that shows this covalent bonds in action. I'm not going to waste your time showing it to you because you can see it on your own, but I do want to point this out since it's up here. Hydrogen is a unique example when we're talking about covalent bonds because hydrogen only has 1 proton and 1 electron. And with only 1 electron, that means it only has 1 electron ring. So we keep saying the octet rule is wanting to fill the outermost ring. But keep in mind, hydrogen's inner ring is also its outermost ring. So again, that innermost ring can hold 2 electrons. Hydrogen only has 1, therefore it needs 1 more to be filled. So therefore, hydrogen can only bond 1 time. I just wanted to point that out really quickly. Let's move forward. All right. That's it for the first two types of bonds, which are ionic bonds and covalent bonds. I'm going to talk about a third type. And before I get into the third type, I will mention one of the big differences between the first two and this one is, like I've said previously, covalent bonds and ionic bonds, it's all about filling that outermost ring, right? It's all about filling that, following that octet rule, right? Fill the outermost ring. Hydrogen bonds are a little bit different. This is not about filling the outer ring. Just keep that in the back of your mind as we move forward and talk about it. So before we can talk about hydrogen bonds, first thing you need to understand are polar molecules. And I brought that up earlier. I said there's two types of covalent bonds. Excuse me, two types of covalent bonds. There's nonpolar and polar, right? And I said we'd talk about that later. So here we are now. I said back then that the polar bond is when the electrons are not shared equally. And that's exactly what I'm telling you now, right? It's an uneven sharing of electrons. Now, also, since electrons have a charge, another way of saying that is it is the uneven distribution of charge, right? Um, Saying the same thing in a different way. So that's the first thing you need to understand is they're not sharing the electrons equally. Once you understand that, then we'll talk about why that is the case, um, and which is what we're about to talk about. Right? They're not shared equally. Therefore, one side is slightly negative, which is the oxygen side, and this side slightly positive. This side slightly positive. You will need to know that, but hopefully, after I explain why that is, it'll be easy for you to remember. Right? Again, like I said, as you can see in that picture, this one water molecule is one oxygen covalently bonded to a hydrogen and covalently bonded to another hydrogen. And as you know, because we just got finished discussing it, I really wish that we wouldn't do that. Anyway, as you know, uh, these covalent bonds are where they're sharing electrons, right? So that oxygen is sharing electrons with that hydrogen. It's also sharing electrons with this hydrogen. Those electrons are being shared. Now, here's where it gets a little bit trickier, but once I say it, and hopefully if you understand it, this will make sense to you. So, what you may not know is that oxygen has a proton number of 8. Hydrogen has a proton number of 1. So that means there's only one proton in this atom. There's only one proton in this atom, and there's 8 protons in this atom, which might be a little bit hard for you to read since it's red. So think about it. If you're an electron and you're a negative electron and you're attracted to positive protons, you're going to be pulled more towards oxygen than you are hydrogen, right? So that's the reason that the oxygen end of the water molecule is slightly more negative than the hydrogen end, right? That's the reason why the hydrogen end is slightly more positive than than the oxygen, because the electrons are hanging out towards the oxygen. It's that simple. So what happens here, and this will make a little bit more sense with the slide after this is going to result in weak attractions between neighboring water molecules. And again, that's not what this is a picture of. That'll be on the next slide. I'll show you a picture of the weak attraction between neighboring water molecules. But before I show you that picture, I just want to point out that, again, this is what we call hydrogen bonds, right? So again, just to back it up and give you the big picture here, ionic bonds, that's when atoms give up or take electrons, right? Covalent bonds, that's when atoms share electrons. Hydrogen bonds is simply a weak attraction between, in this case, neighboring water molecules, but just so you know, and that'll be sufficient for this course, but just so you know, other things can also hydrogen bond. But yeah, but the way we're talking about it is we're talking about neighboring water molecules. But again, anything that has polar bonds can have some degree of hydrogen bonds. Another thing you need to know for the exam and for later in the semester is that hydrogen bonds are the weakest. That will be on the exam. That will also be important when we talk about DNA. So again, covalent bonds are the strongest, hydrogen bonds are the weakest. You need to know that. That will be important. And this picture here is basically what I was trying to draw on the previous slide, right? We have this oxygen that has 8 protons. We have this hydrogen that has 1 proton. We have this hydrogen that has 1 proton. So all these electrons are hanging out near the oxygen more than they are the hydrogen. Therefore, the oxygen has a slightly negative charge, and the hydrogen parts have a slightly positive charge. But again, this first bullet point, the weak interactions between neighboring water molecules, that's this picture right here. So here we have 1, 2, 3, 4, 5 water molecules interacting with each other. And this also brings up two exam questions that I want to talk about, because some people think they're trick questions because they're so similar, but I'm not, they weren't meant to be trick questions. So I'm telling you now that they're very similar and to be careful for them and to not confuse the two. So one question is basically going to ask you, what kind of bond holds together a single water molecule? Right? So let's say we're just talking about this one water molecule. What kind of bond is holding that oxygen to that hydrogen and to that hydrogen? And you can see here that single line, right? That is a covalent bond that holds a single water molecule together. Then there's going to be another question that asks, what kind of bond holds neighboring water molecules together? And the answer is, as you can see here, hydrogen bonds. It's hydrogen bonds that are holding neighboring water molecules together, but covalent bonds that hold a single water molecule together. As a matter of fact, if these hydrogen bonds, oh, by the way, hydrogen bonds are written like that with little dashes. If those were not hydrogen bonds, if those were covalent bonds, right? If we just connect those dots and made those covalent bonds, by definition, these would not be neighboring water molecules anymore. They wouldn't even be water anymore. But if they were all covalently bonded to themselves, as I kind of hinted at previously, that would just be one just one molecule, right? So when they're all together via covalent bonds, it's one molecule. So let's move forward. The next word for attendance will be cat. So write that down. I should see a screenshot also that includes a picture of that cat. And I'd also want to point this out before moving forward. As you can see here at the top of the screen, this is not in your textbook, right? My PowerPoints, I used to use a different textbook. And when I switched over to this new free one, I didn't just start from scratch. I took my old PowerPoints and I updated them. But I left some stuff from the old textbook, including this one. But I will say, as far as the exam is concerned, this slide is a little bit less important, but I still wanted to include it. Just so you know, there are 92 naturally occurring elements. But I'm going to put a little extra line through that just because you don't need to know that. That's not a question I'm going to ask you. For extra credit, feel free to look up. Notice I said naturally occurring elements. So that means there are some unnaturally occurring elements. For extra credit, if you want to, you can look that up and send me a separate email saying, I looked it up, and this is, and according to this source, and don't forget your link, this is how many total elements there are, or naturally occurring, however you want to word it. But anyway, moving forward, the old textbook gave these 4 examples. It was pretty random. I don't know why they chose these 4, but oxygen and carbon, we're going to talk a lot about those hopefully today. But those 2 are important, and you'll learn why shortly. But also they happen to include potassium and gold, and we don't really talk about those much, if at all, in this course, but there you go. But it does bring me to this point, which again is from the old textbook and not yours. And again, this is something I'm not going to test you on because it's from the old textbook, but it is still worth mentioning because this might clear up any kind of confusion. So each element has a symbol that is derived from its English, Latin, or German name. So sometimes it's not confusing. Carbon's symbol is a C. Oxygen's symbol is an O. Potassium's symbol is a K, right? So that might be confusing. Go, why is it a K? Well, it's because it probably wasn't derived from the English name, probably the Latin or German name. Same with gold, right? Gold doesn't start, gold's symbol isn't a G, it's an AU. Silver is AG. Lead is PB. Iron, which is one that we're going to talk about here in a few minutes, is Fe, right? So you don't need to know any of that. I just wanted to point that out because I just didn't want you to get confused when you're looking at the periodic table and thinking this makes no sense. Now you know why. Now, again, this is not from your textbook, But pay attention because this slide actually does have information that I'm going to include on the exam. And like I've said many times, since this is a 100 level course, I like to teach out of the textbook and test out of the textbook. But this is one of those rare exceptions where I'm going to give you information that you need to know from the PowerPoints. It's not in your textbook, right? So look at all your cells, all the different atoms, all the different elements that make up you, there's 25 of them, right? So out of the 92 naturally occurring elements, 25 of them make you up. Specifically, there's 4 of them. I call them the big 4. You're going to hear me say that a lot, and I might even use that terminology in the exam. The big 4 make up almost 96% of your weight. By weight, you're made up of nearly about 96%, which is a lot, right? That's a huge majority. So again, there's 25 total elements that make you up, and almost all of it is just these big 4. And you need to know the big 4: oxygen, carbon, hydrogen, and nitrogen. You need to know the big 4. You might have to study that, but I have a feeling you won't, because if you do the lab, you're going to be very familiar with the big 4. You're going to be drawing them a lot, and they'll be in a table that you fill out. So you'll be very familiar with them. But yeah, you're going to need to know those big 4. I am going to move forward, though, because we're going to talk about those big 4 later. So again, 25 total elements in your body, in your cells. 4 of them are oxygen, carbon, hydrogen, and nitrogen. So that still leaves 21 other elements, right? So what are the other 21? Well, 7 of them are what I call the medium 7. Since we have the big 4, I call these the medium 7. And I'm going to talk about them a little bit, but just so you know, you don't need to know it for the exam. There'll be no questions about the medium 7. But really quickly, here's some examples. Calcium, and again, from your old textbook. Calcium is one of those others, one of the medium 7s, right? As you probably know, calcium is important for your bones and health. It's also important for other things. So for extra credit, on a separate email, again, 1 email per extra credit thing, please, look up what are some other things that calcium is used for. Likewise, even though this is a little bit less important for biology, our course, you can see a list of where you can get calcium in your diet, but are there any other places you can get calcium in your diet? Then there's phosphorus. That's another example of one of the medium 7s. Again, it's found in DNA, but it also has some other purposes, very important purposes. Feel free to look them up and tell me what they are for extra credit. You can find them in eggs, beans, and nuts, whatever. And again, this is not a nutrition class, so this is not very important, but still I'd give you some extra credit if you look those up. Anyway, again, that's 2 examples of the medium 7. Obviously, there's 5 other ones we're not even going to talk about, but I'll list them later, hopefully in this lecture. But again, you do not need to know them. You only need to know the big 4. So we've talked about the big 4. We talked about the medium 7. We said that there's 25 total elements in your body. Well, we still haven't talked about 25. We haven't accounted for them. So that brings us to this, the trace elements, right? So you have 14 different trace elements, which is really interesting because think about it. That's a lot of elements compared to 4 or 7. That's a lot more. Yet, despite that, they make up less than 0.1% of your weight. That's not a number I'm going to ask you to memorize. But just keep in mind that for these 14 trace elements make up a very, very little of who you are. For that reason, they are required in very small amounts. But and when I say required, I mean required, right? They are essential for life. All 14 of them are needed for you to survive. I've got 13 minutes, so I have time to talk about this. Okay, so not only do you need to know that, but I also want to point out some other things that are not necessarily important for the exam or for lab, just for your everyday life. So like I mentioned in a previous video, we have a really big problem with misinformation and pseudoscience. And another problem we have is something I call chemophobia. That's where people try to scare you about something based on your lack of knowledge of chemistry, because some of this stuff can seem scary if you don't know anything or if you don't know much about chemistry. So for example, iodine, right? It's a trace element. This is an example, by the way. So again, you don't need to memorize anything I'm about to tell you here. A deficiency of iodine causes something called goiter, which is an enlarged thyroid, right? It results in an enlarged thyroid, as you can see from this picture. So again, not enough of it causes this issue, but also because it's such small amounts that are required, too much of it is also dangerous, right? Speaking of which, again, for extra credit, look it up. How much iodine is too much? How much is not enough? You can look that up. You can also look up where you can find it and see if there's anything else that's not listed here. And really quickly, before we talk about some other examples of trace elements, before I go back to this idea of chemophobia, I do want to point this out too, right? This is iodized salt. I'm sure you guys have seen something like this at the grocery stores a lot. When I was younger, when I was old enough to know what an ion was, I used to think iodized salt had something to do with ions, right? Because I knew sodium chloride, I knew those were ions, and I knew that's what makes salt up. So I assumed that's what it was, but it's not. We need iodine and generally don't get much of it in our diet. So iodine has been added to salt, right? That's one of the reasons. And I'm gonna come back to that idea here in a second too. But yes, we put elements into our food and into other things because we need them. They are essential for life, and very often we don't get adequate amounts from our diet. Which brings us to this another um, trace element. You need it. This is required for life. It's essential. It's fluorine. You need it, right? We add it to our dental products. We add it to, like toothpaste or mouthwash. We add it to drinking water in most places in the United States for now. We still add it to our drinking water. It does, like the old textbook says, it maintains healthy both bones and teeth, right? It is needed for our health. And I bring this up as a great example, and I'm glad the old textbook included it because this is one of those great examples of chemophobia. Because someone could likely correctly tell you that fluorine is a poison, right? And like I mentioned earlier, everything's a poison at the right dose. So yes, too much fluorine can be poisonous, but so can everything else we've talked about. Iodine, oxygen, right? There is too much of a good thing. So you need to think critically when someone's trying to scare you and say, don't buy that. It's got fluorine in it. Buy this product. That's usually someone's trying to sell you on something. So yeah, think critically, think for yourself. Again, just one great example of chemophobia where someone says, hey, it's a poison and they're putting it in your water system. So be aware of that. Do your own research. And speaking of which, I shouldn't say research. I should say look it up. You won't be doing research, more likely to be looking things up on the internet. But anyway, again, for extra credit, I invite you to look up fluorine, right? How much is too much? How much is not enough? Feel free to write an email, send me the answer to that question, include your sources, and get some extra credit. But again, before moving forward, remind you that's just one of the examples of the small 14. I'm not going to ask any questions about fluorine. All right, so this slide already goes back to what we hinted at earlier. Iodine, remember I talked about them adding iodine to food. Fluorine, even though that wasn't food, it's still added to our water. It's added to our dental products, right? So we're talking about unnatural things, right? So that people try to scare you with that. It's not natural, but sometimes we need to do it. So like I said, iodine, we need to add iodine to salt. And it's generally been a great thing. But one that I haven't talked about is iron. That's another great example. So when you see like a cereal claims to be fortified, that's usually, very often it's fortified with iron. You need iron. That is one of the small 14. That's one of those trace elements that you need, but you do need it, right? That's what helps carry oxygen in your blood. You need it. And it is literally iron. So when you think of iron, metal, that is what it is. It's not like something that has the same name, but it's different. It is iron as you know it. And this brings up a good point, which again is more important for your everyday life than it is for exams. If you click this link, there's a video, and I don't remember which one, but I'm about to describe two different videos. One video shows somebody demonstrating, it's like, hey, this cereal claims to be fortified with iron, but how do we know that? Are we supposed to just take their word for it? No. So let me demonstrate. So they take the cereal, they blend it up in a blender with a lot of water. So it's just a big mush, right? A big homogeneous mush. Then they take a magnet and they put it to the side of that glass blender, and the iron in the mixture comes to the magnet, and you can see the metal. You can see the metal shavings. The shaving sounds dangerous because it sounds like it might cut you, but it's it's smaller than that. But you can see the iron, literally the iron that they had put into the cereal. Yeah, so that's one video. Meanwhile, there's another video that shows the same thing, but the purpose is to scare you. So that it's the same information, but the way it's presented is meant to scare you. So it's one of these ladies, if I remember correctly. She's like, "Do you know what they're putting in your kids' cereal? They're putting iron, or they're putting metal." I probably didn't even use the word iron, even though that is true. It is iron. Probably used the word metal. They're putting metal in your kid's cereal. And then they went and did the same demonstration, did the blender, put the magnet up, and sure enough, there was the iron that had been put in. So everything they just said was true. They are putting metal into the cereal. But that person's saying it like in a scary way, like the food industry is just out to make you unhealthy. But no, that's an example of what they're doing in this case, which isn't always the case, but something they're doing to make you healthy. You need iron. So again, be aware of people trying to mislead you, because a lot of times pseudoscience and misinformation does not necessarily have to be a lie. Like this example I just gave you, right? Sometimes the way the information, the way the truth is presented can be done in such a way that'll scare you. And later in this PowerPoint, but not today. I know I can tell already I won't have time, but probably on the next lecture, there's another example in this PowerPoint of where people try to scare you with chemophobia, right? But even sometimes by using real information, trying to scare you. Anyway, really quickly, this is again not in your PowerPoint, excuse me, not in your textbook. So if you want to study it, you're going to need to get it from the PowerPoint. But I will point out again, of all these 25 elements that we just finished discussing, you only need to know the big four, right? As a matter of fact, that'll be the next word for attendance is the big four. So I should see a screenshot of the big four at the top of the screen. And again, pause it if you need to, but I'm going to move forward. So you need to know the big four. You don't need to know the medium 7. You don't need to know the small 14, but there they are. And really quickly before I move forward, I also want to point out, even though you do need to know the big four, you don't need to know them in this order, right? It's mostly oxygen, followed by carbon, followed by hydrogen, followed by nitrogen. You don't even need to know that. You certainly don't need to know the percentages, right? 18.5, 65, 9.5. I'm not going to ask you any of that. Just know that the big four makes up a large majority. Another thing I'll point out that we'll talk about later, again, when people are trying to scare you with chemophobia, like imagine you hadn't had biology or chemistry. It would kind of sound scary if someone says, I don't know, you shouldn't buy that, that juice from Walmart because, there's copper in that juice, or there's cobalt in their product, or there's chromium, right? All those things sound scary if you're not familiar with them. Silicone, right? When I think of silicone, and I teach biology, when I think of silicone, I think of computer chips, right? So all of this, tin, right? Zinc, all of that might sound scary if you haven't been exposed to it. So you need those things. So again, when someone tries to scare you by saying these things, they'll try to scare you with the ingredients. There's chromium in that food. They're trying to poison you. No, they're not. First of all, they might not have even added it, because a lot of this stuff does occur naturally. Well, it does. Otherwise, humans would never survive. But yeah, so don't, again, critical thinking. Think for yourself. Don't let people think for you. Question things. Let's see. The next section is going to be about water. We got 3 minutes. Let's go ahead and do the introduction. That way, when we get back on Wednesday, we can jump directly into the conversation about water. So again, this is the second of the third main bullet points of chapter 2, and it's all about water. By the end of this, you should be able to describe the properties of water that are critical to maintaining life. So this first slide is more of an introduction than anything else, because we're getting into the important details later. But this is kind of like, before we talk about why water is important, there's just some things to consider that really will help you remember, yeah, water is important. First of all, life began in water. As far as we know, that's where life started. So that's got to tell you right away that life must be important. Water must be important for life because that's where it started. Not only that, but life is about 4 billion years old. You can look up the exact number for extra credit if you want. But let's just say it's about 4 billion years old. But life was in water for 3 billion years before it even came to land, right? So only 1/4 of its existence has it been on land. 3/4 it's been in the water. So obviously life is very much still tied to water. Again, this is not in your textbook. This is again one of those rare circumstances where I'm going to ask you to know a number that's not in your textbook, and this is it right here. Your cells are made up of about 70 to 95% water. That will be a test question. Make sure you know it. Obviously, that's a big range, right? 70, 90, 95%. That's a big difference. Imagine if those are grades. That's the lowest C possible or a mid A or anywhere in between, right? That's a pretty big deal. Uh, so the reason why, obviously, each person might have different levels of hydration, right? You might be completely hydrated one day and completely dehydrated the next day. But also, obviously, you have different cells, right? So the water composition of a bone cell versus a kidney cell versus a brain cell, I don't know, versus a muscle cell, right? There's all these different cells. So obviously, they're going to have different compositions of water. But yeah, 70, 95% is the number that you need to know, which brings me up really quickly before we're done, and we almost are here. Another thing to remind you, and I don't always say this because I really could say it after every fact that I give you, I could say this. So I'm only going to say it every once in a while to remind you. You don't have to take my word for any of this or the textbook. For extra credit, anytime I give you a fact or a number, you could look it up and say, you said that cells are not 70, 95% water. According to this source, it's this, right? And that's good. I want you to do that because I don't want you to just take my word for it. And also, every source you look at is probably going to give some slightly different reasoning, right? Different explanations. So it's good for you. It'll help you learn the concepts to do that. And again, I'll give you extra credit for it, right? So I looked it up, and according to Britannica, cells are made up of 75 to 95% water, include your source, obviously. So then, yeah, you get extra credit, and you've looked it up. And anyway, really quickly, we really are almost done. As a matter of fact, I will leave it with that. And the last word for attendance will be water. But again, before you get off here, remember, you're required to send the email that has a list of the screenshots, and there should be, a list of the attendance words, and then there will be a screenshot that accompanies each of those attendance words. And then finally, you need to ask me one question about the information presented in this lecture. And that's it. Hopefully I'll see you on Wednesday. Have a great week.